Okay, so welcome guys. So in this video, I just want to talk about a proof of the Lorenz transformation. Okay, so this probably the special relativity is if you can understand all the special relativity properties by just if you don't like physics, you can just remember the idea of the Lorenz transformation. Oh, so the idea is that you have, let's say, k and k prime, right? So and then there's a relative speed v among them. Then you have x, y, z, t in the first coordinate, or x prime, y prime, z prime, t prime in the x prime coordinates. And your story is that right, this is called the Lorentz transformation. So x prime, y prime, y, z prime, z, t prime is gamma, I think t minus c squared. Okay, and the gamma is just 1 over v squared divided by c squared square root. Okay, so all of it's called Lorentz transformation. Okay, and so if you're like group theory, then people can say that all the Lorentz transformation forms a group. And basically it's a non-abelian, and more generally people like it call it Lie group. Alright, okay, but in this video I will not talk about group theory, so that's fine. So in this video, the idea is that I just want to prove this. Okay, so before I start, please subscribe to my channel. Okay, so the key idea in the special relativity is that the speed of light is the uniform. The idea is that the transformation first is linear, and the special and the speed of light is universal. So the key idea is that the transformation is linear. The second is that the speed of light is universal, and add some symmetry properties. So basically, if you know 3 of them, it's trivial. Okay, so let's quickly start k and k prime. So let's say v, and then we have x, y, z, t, and x prime, z by t prime. Okay, so the first idea is that let's assume that there's a light, right, c. So that means x is ct, right? So x is ct. And for this one, x prime is ct prime. Okay, right? So that means x minus ct is 0, and x prime minus ct prime is 0. Right? There will be a factor that x prime minus ct prime. Let's call it a x minus ct. And if you can emit another speed of light, another light go to the negative directions, then have this. Right, so the idea is that if you find a, b, then everything will be done. Okay. Right, but we have a property that we can let x prime equals 0 and x equals to vt. Right, this is the idea that if I'm sitting here and I see k prime, right, then the trajectory of k prime is x equals to vt. Okay, so by these two is come from speed of light. Then x prime is 0, right? So you get the minus ct prime equals to a v minus ct, and the ct prime equals to, let's say, b v plus ct. Right, so combine these two. A divided by b is c plus v, c minus v. Okay, so then the idea is that we need to find these two a, b, right? Okay, so the idea is that we can just emit light, right? We can just emit light. Let's say this is k, this is k prime, right? So this is vt, right? And so I can emit light as this is y direction. Okay, I can emit like ct, and the conducting is the ct prime, right? Okay, so the idea is that if you see the Pythagorean principle, then you know the ct squared c squared minus v squared t squared is c prime squared t squared. Okay, so what is this p? The p coordinate p in the k directions. Okay, so in the k coordinates. So in the k coordinates, this is just 0, right? X is 0. Let's say ct prime. Oh, sorry. This is in the k prime, right? So it's t prime. So the time is t prime. And then for the k, we got the right vt, ct what? ct0 and t, right? So by this one, so this is also basically the speed of light is universal, right? So if you count, if you write a distance, you get this one. Okay. So we just put these coordinates in it. Okay, so let's see. So for this one, let's say for this one. Okay, so I just write x equals to vt, right? So I got vt minus ct equals to x prime minus ct prime, right? So x prime is 0, and ct prime is just ct prime. T prime is just t prime, right? So it's basically this one. And then also I got this. Okay, so combine this, we get the c squared t prime squared equals ab. We just times these two equations, so we get the t squared minus v squared t squared. Okay, so combine this one, we get the ab is 1, right? And then we have two equations, a divided by b is c plus v, c minus v. So we have two equations, then solve ab. Okay, so the result will be a is just right c plus v, c minus v, take a square root, b is c minus v, c plus v, take a square root. Okay, so the final, you just put them back. Okay, so we got the x prime minus ct prime is a x minus ct. We know a, and the x prime ct prime equals b x plus ct. So add the length and divide it by 2, then finally you will get this, right? If you add length, you get the sum of these two. Okay, so I think I don't have to compute. But if you do the sum of this a plus b, then you divide by 2, then you will get this one. You will get gamma, right? So gamma is just 1 over square root of v squared divided by c squared. And then also get t prime is gamma t minus c squared. Okay. So for t prime, just use this equation minus this and divided by 2c. Okay, so this is the okay, and by symmetry that you know that y prime should be equals to y, z prime should be equals to z. Okay, so combine all of this called the Lorenz transformation. Okay, so let me just quickly do some more doing more mathematics, doing more algebra. Okay, so more algebraically. Let's define let's define a distance, right? Let's define a distance to be t squared minus that dr squared. R squared basically is t squared minus xy squared. Okay, so one can view a Lorentz transformation is basically a linear transformation, right? So I can define a Lorentz transformation like lambda is just like a 4x4, right? You will change x, y, z, t to another x prime, y prime, z prime, t prime as a linear transformation, such that it preserves these, right? So such that your c squared t prime squared minus s prime y, right? Well equals to original this. Okay. So if you can write this. So this is the quadratic form. On xyzt, right? So or basically you can write this as a, let's define this vector xyzt to be, let's say r. Okay, maybe let's change the notation. Okay, so let's say I just told you x new, right? So analysis can be written as the e dot new x new. Okay, x new, and then e dot new is just 1 minus that's, so x is here, right? So this is let's say 1 1 minus 1 minus 1 minus 1 1. Okay, just for a notation, right? So and this is just this. Okay, so this is the quadratic form, right? So you can use this and get the equation of this one, this lambda matrix. Okay, so from here we know that the lambda, let's say lambda t, if you put a plug in, you'll get lambda eta, then you will get this one, right? So this is your, right? Just write this as a matrix form. So I can write as x t eta x, right? So combine this, then I add an idea is that determine lambda is 1, right? So this is all the okay. So this is the set of lambda. So the key is that these forms are groups. These forms are a group. Okay, I think now the reason is clearly right, because lambda t eta lambda is eta, right? So the first one is that you can easily check that lambda 1, if lambda 1 and lambda 2 both belongs to the group. So let's say let's denote this by Lorenz, the group G, call it Lorenz. Basically satisfy this property, and the determinant of eta lambda is 1. So let's assume that these two are set both in G, and it's easy to check their products in G, right? The reason is that I don't have to compute. So this is idea, right? So if you compute, you get this is also eta, right? So good. Nice. Okay, and also the second one is that so the second one is so the first, so this is the closure, right? And the identity matrix definitely belongs to G. Okay, and the truth is that you can compute inverse, right? Inverse is easy to prove. Okay. Okay, so what's the final one is the associativity. Let's say right. So this is from a matrix algebra, right? So this is the original matrix. So matrix has associativity. Okay, so combine all of this, we know that all the Lorenz transformation forms a group. Right. So ideally, you can easily check that your original Lorenz transformation that usually in the general physics satisfy this property. Basically, the distance in the pseudo manifold is fixed. Okay. So that's a quick introduction for Lorenz group. And the difficulty in the quantum field theory is basically it works for the Lorenz group, the representation of the Lorenz group. So actually there's a Lorenz group is called SO3,1, which is a the algebra notation, and it has a SL2C double cover, and then you can work for the representation of is SL2C. Oh, sorry, it's true of S squared. No, I think it's SL2C, right? So SL2C is compactified SU2. Okay. So probably in several videos, after several videos, or if I have time, I will cover this how to use this double cover to create the representation of SO31 and or basically from the compactified group of this SU2. Okay, now I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.